This is going to be the lecture over section 17.8. We're going to be looking at Gauss's law. Gauss's law is it's a way of drawing a surface that encloses a specific charge or a specific distribution of charge, and trying to determine what the electric flux will be through that. Now I'm throwing around a few terms here that we haven't really introduced yet. So for a uniform electric field with a perpendicular electric field component to the area A that we're going to be looking at, the electric flux through the area is going to be defined. Here's capital Phi. Sub E is going to be equal to the component that is perpendicular to the surface A of the electric field. It's going to be that product. Gauss's law states that the total electric flux out of any closed surface, that is a surface enclosed a definite volume, is going to be proportional to the total electric charge that is inside the surface. So you're going to look at it two different ways. This is one way to look at Gauss's law. This is another way to look at Gauss's law. This is a picture that describes, let's say I've got a surface that surrounds a specific charge. Again, this is supposed to be something that's more robust than Coulomb's law, where you're just looking at point charges. This could be an actual distribution of charge, something greater than just a point charge. So the electric flux through two concentric spheres is going to end up being the same. We'll get to that in just a minute. Okay, Gauss's law is going to be mathematically equivalent to Coulomb's law. But for some problems, it gives a nice, useful alternative approach to calculating electric fields. Coulomb's law allows us to find the field at a point P caused by a single point charge. To calculate fields produced by an extended charge distribution, we're going to have to represent that distribution as an assembly of point charges and use the superposition principle. So Gauss's law takes a more global view. Given any general distribution of charge, we surround it with an imaginary closed surface, a circle or box, what have you. And that's going to be referred to as a Gaussian surface. So the charge is going to be enclosed within that Gaussian surface. Then we're going to look at the electric field at various points on this imaginary surface. And Gauss's law is going to be a relationship between the field at all of the points on the surface and the total charge enclosed within the surface. So Gauss's law is a part of the key to using symmetry considerations in electric field calculations. Calculations with a system that has symmetric properties can nearly always be simplified if we can make use of the symmetry, and Gauss's law helps us to do that. That's one of the things about physics. If we can apply and make something simple, that's what we're going to do. Electric flux. In formulating Gauss's law, we're going to use the concept of electric flux, or flux of the electric field. And we're going to define it, and then we're going to use an analogy of fluid flow that might make it a little bit more intuitive for you. So the definition of electric flux involves an area A and the electric field at various points in the area. So you can see here in figure 17.26, we've got our area A here, and we've got electric field lines that are coming through it. The electric field is going to be going straight through this surface, which is completely perpendicular to the electric field. So the angle here between this and this is the angle between the electric field here and these lines are, there's not going to be, the angle is going to be 0. But in terms of the surface, it's going to be completely perpendicular to it. So that gets a little confusing. I mean, it tries to explain it here. The electric field is perpendicular to A. The angle between the electric field line and a line perpendicular to the surface is going to be 0. In other words, these are going to be perpendicular. Would have been a lot easier for me to say that, but there we go. So we're going to denote the electric flux. It's going to be a new concept here, and you may not have an intuitive feel for that. It's going to be through the area A, and it's going to be the product of E times A. Now, what happens when A starts to tilt? When instead of it coming through in a perpendicular fashion, it actually comes through at an angle that's a little bit less or a little bit more than just 0. In other words, the electric field has an angle that it comes through. You change the formula around. The formula here for the electric flux is going to be EA times the cosine. In other words, you're looking for the part of the electric field that actually is perpendicular to that surface. Maybe a little hard to see here, but if that is going to be your angle, you're looking for the part of the electric field that sort of falls more in line with the tilt of that particular surface. Finally, if you end up turning this surface such that the electric field lines shoot right through the side of it here, that formula still applies, but the angle that the perpendicular surface that this makes with the electric field is now 90. You end up taking the cosine of that, and you end up with no flux. So this is an actual interesting description here of a particular species that actually sort of feels their way around in water using electric field and how objects distort it. Kind of a neat little description there. So this is the definition here of the electric flux. The units are Newton times meter squared divided by Coulomb. And this is the angle between the electric field and the line that's perpendicular to the surface. So you identify E cosine of phi as the component that's perpendicular. A lot of times it's going to be written as such. Now, the word flux comes from a Latin word meaning flow. We don't really look at the electric field as a flow, but the analogy, if we were to look at it as a fluid, like in this case right here, might help you understand that. So imagine that the electric field is going to be analogous to the velocity of flow of water through an imaginary boundary that's this wire here, this wire rectangle. The flow rate through this particular area is going to be proportional to A and V, and it's also going to depend on the angle between V and the line that's perpendicular to the surface here. So if that starts to turn, what's going to happen here to the amount of water that's actually flowing through this? Well, it's going to decrease, because if you start tilting that backwards or forwards, you're not going to have as much area for the water to flow through. And that's what this is attempting to model. Finally, if you end up turning it on its side, there's no way for any of that to go through. And that's going to correspond to the situation that we had here. So that's why we say the flux at that particular point is going to be 0. So that's the model there that we're using to try to describe this. Now there's several problems here. In order to save memory on the system, I will not work those out, but they are there and they're available for you to go through, and I would encourage you to do that. And if you need me to work those out, I can do that and upload that as a separate file. I have no problem doing that. Gauss's law. And Gauss's law is going to relate the net electric flux through a closed surface, could be a sphere, could be anything, to the total charge contained within the volume of the surface. And it was formulated by Carl Friedrich Gauss, a very smart guy. So many areas of mathematics, from number theory and geometry to the theory of differential equations, bear his influence. Statistics is also a place where he did a lot of work. So for Gauss's law, the total electric flux coming out of any closed surface is going to be proportional to the total net electric charge inside the surface according to this relationship. So the electric flux is going to be equal to 4 pi k times the charge that's enclosed. The flux can be independently determined by dividing the surface up into small elements of area delta A, and then performing the sum, basically going around and taking all of those elements of A and then taking the amount of charge that is perpendicular to that surface that's going through, add them all up, and you've got your flux. Sounds easy, right? Yeah. It can be a bit more complicated than that in terms of actually executing it. So it gives us a relationship between the enclosed charge and the field at the surface. And again, the units here should be the same as what they were before. If there is no net charge inside the surface, then the flux is going to be 0. K is going to be the Coulomb's law constant, and the perpendicular electric field is the component represented with E and the little perpendicular symbol there. Even if the electric flux is equal to 0, the electric field is not necessarily 0. So if you go through and if you try to develop Gauss's law, you start with a field due to a single positive point charge. The field lines radiate out equally in all directions, and we place this charge at the center of an imaginary sphere. We draw this sphere because it's the easy Gaussian surface. It's got a radius r, so the magnitude of the electric field at every point is going to be given by this, which we've kind of gone through before. At each point on the surface, the electric field is perpendicular, and its magnitude is the same at every point, because it's a point charge, radiates isotropically. And the total electric flux is just the product of the field magnitude and the total area, which we had looked at before. We know what the area is. We know what the electric field is. This is what it comes up with. So the flux is going to be independent of the radius of the sphere. Doesn't matter how big it is. It depends only on the amount of charge that's enclosed by the sphere. So you can also interpret this result in terms of field lines. If you look at two spheres here with radius r and then something that's twice that radius, according to Coulomb's law, the field magnitude is 1/4 as great on the large sphere as it is on the smaller. So the number of field lines per unit should be 1/4 as great in order to keep it in line. But the area of the larger sphere is 4 times as great. So the total number of field lines passing through the same is going to be the same for both spheres. I need a little development. This can be generalized to any closed surface surrounding an electric charge. So we imagine the surface is being divided into small elements. If the electric field is perpendicular to the particular elements of the area, then the number of field lines passing through that area is proportional to this. In other words, to the flux through A. If it's not perpendicular, then we'll take the component that is perpendicular, and we'll call that E perpendicular. So the number of field lines passing through delta A is proportional to this. And to get the total number of field lines, we add up all of those products. And this is what we come up with. So these are the generalized arguments as to how this comes about. And it continues to go on and on and on, but still produces the same result. So again, you've got several different problems here to work through. I would encourage you to